Section 10.7 is going to actually combine a couple of things we've talked about in Chapter 10 so far. It's going to combine the conics that you were working with last time, ellipses, hyperbolas, and parabolas, with polar coordinates that we had worked with before, right before that. So to start with, I'm going to give you a little bit of motivation behind what's happening here. If we have a fixed point P called the focus, and we have a line not containing P called the directrix, we can consider the set of all points whose distance to the focus is a constant multiple of their distance to the directrix. So instead of them being equal distances away, they're a constant multiple of distances away. The constant multiple E is called the eccentricity. And if E equals 1, then this description, aside from the new word eccentricity, is exactly what we saw when we did parabolas, right? Talking about one focus, we're talking about a line being the directrix, and we have the same definition we looked at before, with the eccentricity being equal to 1 for parabolas. Okay? But this can be extended, if we're looking at this, to the other conics sections by changing the value of E. That is, changing the constant multiple of the distance to the directrix. Sorry. The distance from the focus, there we go, to the directrix. So in particular, what we have is we have Theorem 7.1, and it says the following. If we have a set of points whose distance to the focus is a product of the eccentricity and the distance to the directrix, then we have an ellipse if you've got a number smaller than 1. Notice E is already positive back here. Make sure I notice that, right? E is already positive, so we have an ellipse if the value is between 0 and 1 or smaller than 1. We have a parabola if E is equal to 1, which we already said. And then we have a hyperbola if E is greater than 1. We don't have less than 0 because the eccentricity is actually defined to be something related to distance. So there's not negative distance. So we don't have that possibility. Yeah. Any other questions? All right, I've got one more theorem for you, and this is the theorem where you're going to have all the formulas that are probably going to end up on your note card. This is Theorem 7.2, and I'm going to just read through it with you, and then we'll talk a little bit about it. So if we have a conic section, eccentricity greater than 0, the focus is at 0, 0, and we'll talk about what happens when the focus is a little bit different a little bit later. And we have the directrix that's indicated below. And then we have these 4 polar equations. They are all very similar, right? Tell me something you're noticing different about them. Some of them have sine, and some of them have cosine, and some of them have +1, and some of them have -1. Okay? And those pieces are changing based on how the directrix is defined. So we've got 2 of them that have vertical directrix, right? X equals. And then we have 2 of them that have horizontal directrix, which is y equals. And then the difference is whether or not the x equals is a positive number, or the y equals is a positive number, or whether it's a negative number. We get a different image. So that very slight change in the formula, the sine or the cosine, the plus or the minus, gives us a different kind of directrix, or it comes from finding a different kind of directrix, whether it's vertical or horizontal, and whether it's positive value or a negative value. Promise we're going to come back to the focus 0, 0 in a minute. We're going to see an example of something with that later. For the most part, though, the focuses we're going to be working with are at 0, 0, just so you know. I debated whether to show where these formulas are derived from. Your book shows one of them. And what I decided to do is sort of wave my hands a little bit and sort of describe to you where it's happening from. Does everybody have these written down before I switch to the next slide? Okay. These formulas are actually coming from the equation the square root of x squared plus y squared equals E. That's the eccentricity. And then d minus x is the distance that we're referring to between the directrix and the axis. Yeah, we'll say it that way. If we use the substitutions with polar coordinates, of course, you recognize something like the x squared plus the y squared is actually what in polar coordinates? What's x squared plus y squared? It's r squared, right? And then we've got it square rooted, so the left-hand side would become r very quickly. Yes? Now, that's a little trickier because we've got that x on the right-hand side, so we can't just automatically make that just plug in right there. And so if you're interested in seeing where they're deriving one of these formulas, the book actually derives one of them. It doesn't even derive all four of them because the derivation is so very similar for all four of the different ones. But you can imagine over here what's happening. It's you're getting that r on the left, you're getting that e times d, and then the cosine or the sine is coming from the fact that you have this y, or this x value right here. And if you were working with the equations that had the other directrix, you would have a y there instead of an x. So that's what's happening. And y and x, of course, are related to the r sine theta and r cosine theta from the polar coordinates. So that's where those pieces are coming from. Let me show you how to use these formulas because that's the part that you're going to like. We've got an example. It wants us to find the polar equation with a focus at 0, 0. I told you that you're going to have the focus at 0, 0 for the most part. It's got the given directrix and eccentricity. We're supposed to find two things. We're supposed to find an equation, and we're supposed to graph it. Right? So the first suggestion that I'm going to make is that it would be wise for you to be able to look at this and tell me what the shape is without doing anything else. How are we going to be able to do that? How do I know if it's a parabola, a hyperbola, or an ellipse? The e value, yeah, the eccentricity here tells me it is a 1.2. So theorem 7.1 tells me that this is a what? This is a hyperbola. Okay, so I should be able to say that without graphing anything here. I'm going to show you how to graph it in a minute, but we should be able to make that claim. And then we're going to use theorem 7.2. So by theorem 7.2, which equation is this? Taking a look back at the different options here, it's going to be something of the form ED over so forth, based on what the directrix and based on what the directrix is, the equation of the directrix. So the equation of the directrix on number 1 is x equals 2. Which case am I in? The first one, because I've got x equals, right? And because the x value that it equals is positive. So this is case number 1, so to speak. So by theorem 7.2 I, or part I, we have r equals. Now what goes on top is the eccentricity times the x value. I know the formula says d, but d is measuring the distance to the x value. So this is going to actually be 2 times the x value, or sorry, 2 is your x value, times your distance, which is, or eccentricity, which is 1.2. So I guess I actually wrote those backwards of what the formula said, but commutative, right? No problem? Multiplication is commutative? Excellent. All right, below I actually have e, so that's my 1.2. And then what trig function is this one? It is cosine of theta. And then is it plus or is it minus 1? It's plus 1. So my r equation, my polar equation for this is actually 2.4 over 1.2 cosine theta plus 1. I looked in your book, and I looked in a couple of other calculus books to make sure that it wasn't just something weird that yours was doing. And there doesn't seem to be any emphasis on being able to graph this by hand. So that's good for you, right? Yeah, absolutely. So I want you to grab your calculator. We're going to graph this equation in polar, so make sure you're in polar mode, the r equals. We're going to plug this into our calculator, and the image we get should be a what? Better be a hyperbola. I do expect, since I'm letting you use your calculator for doing this, that your graph should look fairly accurate. So you should be able to zoom in and make sure that you've got the pieces crossing the x-axis and the y-axis at approximately the right places, those kinds of things. You will see something funny happen in your calculator, though. So tell me what it is that's funny that you think I might be referring to once you see it. Yeah. Say that a little bit louder. I think it was you, Jordan, right? Oh, sorry, Nathan. Yes, it does. It actually graphs the asymptotes in there, doesn't it? So when you draw them on your graph, I think drawing your asymptotes makes sense. Your calculator did it for you, but I would prefer that you not draw it in as solid lines because it really isn't part of your graph. You've drawn asymptotes before, and how have you drawn them before? Dotted lines. So we're going to do dotted or dashed lines in order to draw those as well. So take a look. Your asymptotes seem to be crossing at approximately what value? What's it look like? Can you tell? The asymptotes cross what x value? They cross on the x-axis. Let me say that first. Right? I'm not imagining that, am I? No. Okay, good. Thank you, Caleb. What x value does it appear to be crossing at? You can manipulate your window, zoom in, zoom out, change your windows, x min, x max, to look for what you need. 6, I think, is what I wrote down. Does it look like 6 okay? So we're going to do that over here too. So they're going to cross at 6. I don't know if I have, maybe I do. Let me see. All right, I think I have dotted lines in here, so mine are going to look a little bit more dotted probably than yours. At 8?
Yeah.
I'm getting 6s, I'm getting 8s. Everybody double check your entry. You have 6 now. All right, Joel. That's going to take a look. All right, so draw those asymptotes in there crossing at, we've decided 6, right?
That's not exactly 6.
Pretty close?
Mine's between 6 and 7. It's probably close to 7.
Okay, 6.5. My image is not good here, too. Let me move this over. Okay, so we think 6.5. Is that what you're saying? All right, so 6.5 it is. I'll go with that one. It's about right there on my graph. I'm not looking for absolute perfection, but it should be pretty close. There shouldn't be some sort of weird disparity between what you have going on. My picture's not even very good because of the way this is drawn dotted, but yours will be better, I'm sure. Yes? Sure. You need the whole denominator in parentheses. Otherwise, it's doing the division first and then multiplying. Anytime you have more than one piece in your denominator, whether it's addition or even multiplication, your denominator has to be in parentheses. Did everybody else have that in theirs when they were working? So maybe you have the cool math type so it doesn't automatically for you. But what are the focus, not focus, there's 2 points when we were drawing our hyperbola that were like the minimum and the maximum as you were looking at it from sort of moving from one piece to the other piece. Where are those located on your picture? Where does it appear? They're along the x-axis. Let me say that first, right? Yep, x equals 1. Where else? 12 is the other one. Okay, so let me see if I can get my picture out that far. I think I've got that at 12. We'll pretend it's at 12 if it's not. And then they're drawn out from there, right? And they're supposed to be getting close to the asymptotes on the edges. That's the whole point. So we get something that looks something like this. So the center appears to be at about 6.5, right, where those asymptotes cross. And then we have these vertices, that's what we call them, these maximum, minimum kind of points at 1 and 12. What do you think? Is that okay? Let's try another one. Same directions, problem number 2. What graph is this? Hang on, which one is it? Yeah, this is an ellipse. By Theorem 7.1, this is an ellipse. And then we're going to use Theorem 7.2 to create our equation. So which part do we have on Theorem 7.2? We have a directrix y equals, and it's y equals 2. So which part am I on? 1, 2, 3, or 4? Which one? 3. I've got the line y equals, and I have a distance, a d value rather, for my directrix that's positive. So I'm on part 3. So I've just got, oops, sorry there, my theorem 7.3, I've got R equals. I've got the two values multiplied, so that's the 2 times, in this case, 0.6, divided by eccentricity, 0.6. Is it sine or cosine? Sine. Is it plus or minus? It's plus 1. So my equation is actually 1.2 divided by 0.6 sine theta plus 1. And we're going to graph it. Make sure that denominator's in parentheses like last time as well. So as we're looking at this, we're kind of looking for the key points we had before when we did ellipses, which were the vertices, which are along the major axis, and the other corresponding points that were kind of like vertices along the minor axis, and a center point as well. And we should be able to find the center point, even though it's not a part of the graph, by simply counting how far some of the vertices are away from each other. So I'm going to start by asking you what the center is. So look at that and see if you can piece together from your picture what in the world is your center.
Yeah. I'm guessing.
Wait a second. So you're getting it at where?
I'm guessing it's 0, -1.
At 0, -1?
Ish.
Is that what it looks like to everybody? Okay, where do you, let's talk about where do we cross the y-axis. What are your pictures on crossing the y-axis right now?
Why?
Yep, where does your graph cross the y-axis?
Below 1 and
Negative
1
3
and
and
-3.
minus.
At +1?
More like
it's not quite positive.
Not
yeah,
quite.
positive 3/4 or so.
Okay. I think I must have had a graph issue when I was doing mine because I'm getting something slightly different on my picture, but that's okay.
Yeah, it's positive.
So a little bit below 1, and then what about the negative one?
It'd be -3.
About -3?
Yeah.
Okay, that looks good. So if you take mine's purple, my purple dot in the middle there at -1, and you go out from there in both directions, you should be balancing how far out you go, right, along that axis. How far out are the corners of this thing, if you will, corners? 1.5?
I got 1. 1, -1. You're talking about X.
On the x-axis, it doesn't look.
Wait, what are you?
No, not on the x-axis, from the center point, from this point right here that we labeled.
-1. Yeah.
So a little bit more than 1,
Yeah.
like this. Sorry. Let me do this. In both directions, then?
Yeah, that's what I got.
1.5?
Yeah. Yeah.
Oops. Okay. The picture looks a little lopsided. The thing that looks a little bit weird is that it looks like from the purple dot, which is the center, I've gone down fully 2 points, and I've only gone up 1 3/4, so it's a little bit lopsided somehow in here because we're estimating. But aside from that, this is an ellipse. It looks something like that. Looking like it's going out about 2 from the center up and down, and about 1.5 from the center left and right. You guys good with that? Okay. Last question in this section. By Theorem 7.1, what is this? This is a parabola. By Theorem 7.2, what part of that theorem, rather, are we going to use? We've got x equals -2. Yep, this is part 2. But an x equals a negative value this time. So r equals, we've got our -2 times our 1 for our eccentricity and our d value on the top. What's going to go in the denominator? Yeah, if you want to put the 1, you can do that. It's cosine theta then, and it's -1. Is that right? Yeah. So this is r equals -2 over cosine of theta minus 1. And you're going to take yourself a graph of this. This one I think was fairly clean on where it's crossing things, so you guys confirm for me if that's the case. So tell me some feature that I should put on my graph here. -1, 0, like this. Okay, so it's got a vertex at -1, 0. Good. What about crossing the y-axis? Where's it going to cross the y-axis?
0, 2, and 0, negative.
So somewhere around 2 and -2, or maybe even exactly 2 and -2. And then we're going to connect these. Looks like this. This one's a fairly wide parabola, actually. All right, any questions on that one? All right, we have one more example. You ready to take a look? This last example, what looks different than what you've seen before on this? Theta minus pi over 6, that's a little weird. We're going to talk, it's not going to be super obvious on this. Well, it is a little obvious. You'll see what's happening with that pi over 6 in a moment. What else do you see that could be helpful? You should be able to tell from this equation what graph you're using. That's actually based on the combination of 7.1 and 7.2 together. Can anybody tell me what graph you're using and how you know? This is a hyperbola. How do you know? James, I heard you say it loudest, so.
Because you've got on the top it should be e times x, and you know that the e is 2 from the bottom of it, so x has to be 2.
Okay. And in particular, we could even just look, we do know that the x is 2, you're right. We could just look at this being the eccentricity itself, because the eccentricity is what tells us, right? The eccentricity is 2, and so since the eccentricity is 2, we've got a hyperbola, right? Now, I didn't actually state it. I assume you guys probably read it. It just says to graph and interpret the conic section. The fact that it's a hyperbola is part of that interpretation. We're going to graph it. Your calculator will graph it just fine. And we're going to use our calculator to make one more comment about the interpretation as we look at this. So let's go ahead and graph what you're seeing happen here. And tell me if you can, what about this looks different than the graphs we saw back on 1, 2, and 3? Does have a vertical asymptote. Roughly where? So a little bit more than 2 is what you're finding?
Yeah.
I hope everybody's in radians. Okay, so that's sort of unusual. The asymptote we saw in our last hyperbola wasn't vertical. What else? It has another asymptote, right? Is it horizontal? No. Where is it? What's it look like? Sort of a diagonal. It's pretty flat, actually, by comparison. Whoops. Let me try that again. It goes through about where on the x-axis? Let me plot that before I do it. At about 2-ish?
Closer to 3.
About 4.5.
Yeah, how about like 4.5?
Yeah, we definitely have some difference of opinions. Should we find it?
Definitely 4.5.
Definitely got 2, definitely 4.5. Okay, let's take a look at the calculator so you guys can, something's happening. Wonder or not. Let's see the equation.
You should definitely look at it.
What is your window?
Yeah, that's 4.5.
Yeah.
Yeah, that's 0, 1, you got it.
Yeah, I know. like it's not, you're saying at 4.5? Is that what you guys were saying?
Yeah.
Like where
Yeah.
crosses the x-axis?
Are you talking about the?
Crosses the wax.
We were talking about, she said where does it cross the x-axis?
Yeah, I was talking about the x-axis.
Oh.
No, yeah, the x-axis.
Oh, 4.5.
It should be crossing the x-axis the same place it crossed before, right? And then at the y-axis, you're getting it at about 2.5?
Yeah.
Okay. I think you guys, we were just,
So it wasn't.
everybody was saying the same thing, we were just using the wrong
She
words.
asked the
I'm
x
sorry.
and you said 2.
Okay, so it's crossing the x-axis, where did you guys say? 4.5?
4.5.
4.5. And the y-axis at about 2?
Fight all of you.
No.
2.5?
It looks like
2.5. Oh yeah, the y-axis.
no.
What are you talking about?
Y-axis or something.
Yeah, 2.5.
Thanks.
All right, it wants to use things
A little
funny.
bit more to do
As long as Joel's wrong.
All right, it won't let me draw what I want to draw for some reason. It's not letting let me draw it. So, what about the y-axis below on the negative side? Negative 2.5?
There's no.
Oh, no, there's not. You're right. We already did them both. Okay. And then we've got the two pieces. What about the graphs themselves, the ones that are actually part of our equation? Where do they cross somewhere? Can you give me something?
Like, well, 2 on the y-axis.
2 on the y-axis looks good. Can you tell me on the x-axis on that piece, roughly?
1.5-ish.
Okay.
Yeah.
So we'll draw in that one right there. So this graph looks something like this. What about the other one? I'm only going to have an x one. Can you tell?
5.5. Yeah.
Yeah. Okay. Sounds good. Something like this. What's different about this visually than the hyperbolas we have seen up until this exact example right here?
It's like the slant end has to do with
It looks like it's slanted, right? It doesn't look like it's opening left, right, and up, down. It sort of has a tilt to it. Any guesses by how much it's tilting? Tilting by an angle of pi over 6. It's exactly right. So this over here, when we were describing it, says this is a hyperbola. And I will tell you that I don't think the back of your book actually talks about the tilt, but that's kind of the whole point in this particular section is they're all going to have some sort of a tilt based on an angle measurement. So this is tilting, and this is a hyperbola. I like the word tilting. You guys were using it, I am too. So we're going to tilting pi over, let's say tilting at an angle. Pi over 6. That doesn't look good at all. Let's try it again. Pi over 6 radians. And it's doing it counterclockwise, right? The same way we measure radian measure, but just so that we're clear, I'm going to write counterclockwise here. Right, it's a positive pi over 6 radians. That happens anytime you subtract the value from the angle measurement itself or anything like that. You're always moving in the positive direction, and a positive direction here is counterclockwise. Any questions on that one?
So like what you just wrote is like the interpretation.
That's the interpretation.
His calculators checked up.
Is yours all messed up, James?
Okay, can you take a look at it?
Yeah. All right, any questions on this before I do that, though? All right.